Hello everyone, welcome back to the training. Am I clearly audible to all of you? That's great. I'll quickly share my screen and we will continue our discussion on amazing protocol OSPF. In the session yesterday, we tried first a basic configuration of two routers, R1 and R2, and we added both of them into the area 10, right? And connected them over the network 12.10.1.0/24. Then later on, we discussed how we can connect R1, R2, and R3 in the area 0, right? In this deployment, we looked at how OSPF can be configured using the network command. In this deployment, we looked at how it can be done using the interface commands. Now is the time when we discuss a bit more about OSPF and we try configuring basically the multi-area configurations of OSPF routing protocol. The very first thing that we are going to discuss today is the OSPF neighborship stages. Yesterday, when these OSPF neighborships were coming up, did you observe it used to write neighborship state changed to full? In the CLI logs of your router, whenever neighborship would come up, you will see a log saying that neighborship state changed to full. So today we are going to discuss and understand what all are these different neighborship states and how OSPF performs or what responsibility does a router fulfills in each and every given state. So let's see how many neighborship states do we have. When we talk about connecting two routers in OSPF, there are certain neighborship criteria which we have to fulfill, right? Let's say I am willing to connect R1 with R2. The very first thing that I need to fulfill is that they should be a part of same subnet. Assume that they are connected on the subnet 12.10.1.0/30. Second thing that I need to fulfill is that their area should be same. So let's assume that they are participating in the same area 10. Third thing is their timers should be same, which by default is going to be same for both the routers. The hello and dead time by default are 10 and 40 seconds respectively. So they'll be same in the case of these two routers. And I fulfill all the three criteria, so I can say my neighborship would come up. Now this neighborship goes through different stages of neighborship, and at every stage, OSPF fulfills certain responsibilities. Let's talk about these stages one by one. The very first stage of OSPF neighborship is called down state. The state 1 of the OSPF neighborship is down. This is when your OSPF is not yet enabled on the device. Clear? So when you just have connected the routers and OSPF hasn't been enabled on the device, at that time you can say that the state of neighborship is down. After that, you enable OSPF on the device. You get into state 2, which is called init. In the state init, initialization happens, OSPF is enabled, and a hello message is generated. So on the router where you will enable OSPF, that router will generate an hello message for the connected devices. And this hello message will be sent on the multicast address 224005. Clear? After that, when we receive back a hello from my neighbor, we get to the state number 3, which is called two-way. Two-way means that the connectivity is trying to get established from both the ways. So this is where the reply from the hello is received from my connected neighbor. Inside the hello message, we find the information about network, area, and timers. So we compare all these parameters and try to figure out if the connected device is eligible to become a neighbor or not. Make sense? So when I'll exchange hello messages between R1 and R2, I will try to figure out if my area, my subnet, and my timers are same or not. If everything is found to be correct, we consider the connected device as our neighbor and put the information about it into the first table of OSPF called neighbor table. After this, we get into the state 4, which is called as Xstart. In the fourth state of OSPF neighborship, the master and slave elections takes place. Basically, we decide who will send the routing details first, whether R1 will send the routing details first or whether R2 will send the routing details first. That election takes place here. And that election takes place on the basis of highest router ID. I'll tell you how router IDs are configured. When we speak about OSPF router ID, we consider the router ID on the basis of 3 preferences. The very first preference is given to the manually configured router ID. Remember, in the lab guide yesterday, there was a command to manually configure the router ID. So if there is a manual configuration of router ID, we will consider that as our router ID. But what if there is no manual configuration? In that case, we consider the second preference will be given to the highest loopback interface IP address. Loopback interfaces are the virtual interfaces like we have discussed yesterday. So whatever loopback interface will have the highest IP, that will be considered as the router ID of that router. If let's say the loopback interface is also not there, Then we look at the third value, which is highest physical interface IP address. Clear, guys? If we put a manual router ID configuration, we will consider that as the router ID of that router. If there is no manual configuration, we try to find out highest loopback IP. If let's say loopback is also not there, then we jump on to the third thing, which is highest physical interface IP address. This physical interface needs to be active. So I can say highest active physical interface IP address. If the interface is down, we will not consider it as our router ID. Now, between these two routers, whosoever will have the highest router ID, that will initiate the process of routing exchange first. If I talk about R1 and R2, let's assume that on R1, I have configured a manual router ID configuration with a router ID as 1.1.1.1 and router 2's router ID as 2.2.2.2. So what do you think? Who will win the election? R1 or R2? R2, correct? So in this case, when we'll exchange the network information, R2 will send the network information first. Clear? We have a question, how a IP can become a router ID in case there is no manual configuration. Like I told you, here I have given a manual router ID configs, right? But what if this configuration is not there? Then we will check if R1 and R2 have some loopback IP. Okay. We'll try to find out if loopback interface is there. But let's say loopback is also not there. There is no manual configuration of router ID. We just have these two routers connected to each other on 12.10.1.0 network. So next preference which I give is to highest physical interface IP, right? So I'll compare 12.10.1.1 with 12.10.1.2, where again router 2 is winning. So R2 will initiate the network exchange or network information exchange in this given domain. Clear, guys? So after we have decided who wins the election, who becomes the master, we get into state 5, which is called exchange. So we get into the state 5, which is exchanged. This is where the routing details are exchanged between the devices. As per the discussions, we have discussed that R2 will have the IP 12.10.1.2 here, R1 will have the IP 12.10.1.1 here, which will also become their router ID as there is no manual configuration, as there is no loop back here, right? So in this case, R2 will win the election. That means R2 will initiate the exchange of routing details first. So R2 will send routing details first to R1. These routing details will be acknowledged by router number 1, and R1 will also send routing details to R2. These are then finally acknowledged by router 2. This is how the routing updates are exchanged. Clear, guys? Yes, Sayed. If there is no manual configuration, I have mentioned already, highest loopback IP will be considered as router ID, or otherwise highest active physical interface IP address will be considered as router ID. The routing details are exchanged with a packet called DBD. DBD stands for database descriptor. Clear? And these database descriptors are used to create another table of OSPF, which we discussed yesterday, called database table. So this information will help me construct another table, link state database table. Then we get into state number 6, which is called as loading. And this is where the neighbors compare their database table with others. For example, I and let's say Mr. Rahul have created a neighborship. We were able to exchange information. We constructed our database tables. Now in the state 6, I will ask Rahul to compare my database table with Rahul's database table. So I'll check if Rahul and I know the same information or not. Clear? If in case there is some information which is missing in my database table but is present in Rahul's database table, so I will request Rahul to share that information with me. And we request that using a message called LSR, which is known as link state request. Now, when I am asking about some network from Rahul, Rahul will also give me a reply, right? That reply is known as LSU, which is link state update. Once that is done, we get into the final state where we can consider the neighborship to be established, which is the state number 7. Called full, where basically we consider the neighborship to be completely up, and we consider that now these devices have completely exchanged the database information with each other or the network information with each other. This is how the whole 7 states work together, or this is how the router crosses all these 7 states to get into the final state of OSPF neighborship called full. Let me know what questions or doubts do we have before we continue the discussion ahead. when happens LSR. So Nicholas, assume that I have become neighbor with you. Okay. Now I and you will compare our database table. And if there is some information which is not present in my database table, but is present in your database table. So I will request you that information using link state request. Clear? This is how the 7 states of OSPF neighborship are used. Now, let's understand something about different types of networks. Did you observe when I was creating this cable connectivity between R1 and R2, I used a zigzag connectivity, right? I'm putting it like this. This type of connection is used for representing serial cable. Okay. Serial cables can only allow two devices to connect on a particular segment. That means this connectivity is a point-to-point connection. But that's not always going to be the case. Okay. There can be a multi-access network where I am using Ethernet cable or I am connecting multiple devices together, right? So let's see what happens in that situation. Assume that instead of now just two devices, I have four routers connected with a switch. This is my switch. And there are four routers connected to it, R1, R2, R3, R4. Now, guys, in order to exchange the routing information with everyone, my R1 will create some neighborships. R1 will create a neighborship with R2. It will require a neighborship with R3 and will also require a neighborship with R4, right? Similarly, if I talk about R2, R2 will require a neighborship with R1, then with R3 and with R4, correct? Now for R3 also we need a neighborship with all of them. With R1 and R2 I already have a neighborship. I will just create neighborship with R4. If we try to count the number of neighborships that we have established for four routers, it's going to be 1, 2, 3, 4, 5, 6. So four routers would be able to operate with 6 neighborships. And there is a formula also for this, which we can use for calculating. Just give me a minute, please. So the formula to calculate the number of neighborships required is n multiplied by n minus 1 divided by 2, where n represents number of routers. So if I have 4 routers, how many neighborships would be required? 4 multiplied by 3 divided by 2. 12 by 2, that means 6 neighborships. Now 6 neighborships might sound like a very less number, right? And it is also. But what if I have 10 routers? If I have 10 routers, then the number of neighborships that we will require on a multi-access network would be 10 multiplied by 9 divided by 2, 90 divided by 2, 45 neighborships. That's way too much. Every neighborship will require some resources, some CPU, some RAM to process the packets and the information, right? And if I have, let's say, 10 routers, then they will somewhere require 45 neighborships to completely operate, which is a very huge number, right? Similarly, if let's say I talk about, let's say, 20 routers, then 20 would require 20 multiplied by 19 divided by 2. That's going to give me 10, right? So 190 neighborships. So it is definitely not the way how we can use OSPF for multiple routers. This is where the entry of designated router and backup designated router happens. What is the responsibility of designated router and backup designated router? Let's understand. Let's say now you have one designated router, one backup designated router connected to your switch. And this switch also connects with two more routers. These devices will be called as DR others. Okay, that's the first thing to remember. Second thing to remember is all of my DR other will maintain neighborship with designated router as well as backup designated router till the state 7, which is full. So I will maintain a full neighborship with both designated router and backup designated router. That means I will share my routing information with designated router as well as BDR. But when I talk to a DR other, I will only maintain a neighborship till the state 3, which is two-way. Now, what was happening until two-way? If you see, until two-way, we are only exchanging hello messages. No routing information is being exchanged, right? So this brings us the clarity that with my DR and with my BDR, I will exchange my routing information. But with a DR other, I will just say hellos. I'll just exchange hello messages. What would be the benefit of that? The benefit is that now it is completely the responsibility of DR to send the routing updates to everyone who is connected in that area or in that segment, right? I don't have to maintain full neighborship with everyone. Earlier, when I was connecting without DR or BDR, I required so many neighborships to exchange the routing information. But now I just require full neighborship with DR and backup DR. Rest with everyone, I just need to exchange hello messages. That means I'll just maintain my neighborship till state two-way. Does that make sense to all of us? So DR and BDR will have all the routing information of the connected devices, and they will be responsible for sharing it with the other routers. Like I said, every router will maintain a full neighborship with DR and BDR. So just like R1 is maintaining a full neighborship, my R2 will also maintain a full neighborship like this, right? And the routing information that I receive from R1, I will forward it to R2. Make sense? I'm repeating again. If we don't use the concept of DR or BDR, the routing information exchange will require so many neighborships. For example, for 4 routers, I required 6 neighborships. For 10 routers, I required 45 neighborships. For 20 routers, I'll require 190 neighborships. Every neighborship that we have to maintain will require some resources, and we can say the RAMs and CPUs of my router, right? Because we have to share the routing updates, we have to process the routing updates and everything. So what we did, we introduced a master of the topology, DR and backup DR. Just think of DR as of now. I said I will maintain my neighborship with DR up to the state 7, which is full. That means I will exchange routing information with DR, right? But if there is a normal router just like me, I will only maintain my neighborship till the state 3, which is two-way. I will not share routing updates directly with that neighbor. All of my routing information will be transmitted to that device via my designated router. Clear? So instead of having the load on all of the devices, what we said, I will put one powerful device who will do this job of receiving updates from everyone and sharing it to all the other connected routers. That is going to be my designated router. Now, because there is a key responsibility to this particular router, we also make sure that there is a backup to it, which is a BDR, who is also doing the same job, but will only get into picture if DR is no longer available. So if designated router goes down, my BDR becomes DR, and because it is also receiving all the routing updates, it will also start processing those updates and sharing it with the connected routers. What questions or doubts do we have? Exactly, Pooja. Now the question is, who will become designated router and who will become backup designated router? Basically, what is the election process of this? The DR and BDR election depends on two things. One is priority value. This priority value can range from 0 to 255, and by default, it will be 1. Second is highest router ID. If in case the priority value is same on all the routers, what do we look at? We look at highest router ID. Clear, guys? There is one more thing to always remember about the elections, which is if the priority of a router is set to 0, then that router never participates in DR and BDR election. Clear, guys? So if you have set the priority of a particular router as 0, it will never become a designated router or backup designated router. We have a question how to know the router ID. Router ID, like I told you guys, will be considered in these preferences. First, we give the preference to manual configuration. Then we look at the highest loopback IP. Then we look at the highest active physical interface IP. How to check the router ID of connected neighbors? We use the command show IP OSPF neighbor, like we discussed yesterday. Show IP OSPF neighbor tells me about the connected neighbors and their router IDs. It will also tell us who is designated router, who is backup designated router. Any questions or doubts before we jump on to the lab part? We can change the priority value. There is a command for that. I'll show you that. No worries. Any other questions in understanding the concept? Okay, what is LSA? LSA stands for link state advertisement. Remember, I told you guys about these DBD packets, database table, which is maintained and created using DBD. Inside DBD, we have the network information as LSA, link state advertisements. Clear? For priority, lower is preferred? No, the highest priority will be preferred. Whatever router will have the highest priority, that will be selected as DR or BDR. If two routers have same priority, we will check the highest router ID, correct? Yes. When will BDR get into picture? Whenever DR goes down, my BDR will start operating as DR and will change its role to designated router. When this becomes a designated router, some other router might get selected as BDR. Any other questions? Okay, we have a great question here. What will happen when the original DR will come back online? Will it again take the role of DR? No. After DR and BDR election is done, so if a router recovers back or gets added into the scenario, we do not change the DR or BDR. Okay. So if the elections have taken place already, we will not modify anything in that. LSA is inside DBD. database description. PDR is simply a backup to the designated router. Whenever DR fails, whenever it will go down, backup designated router will take the responsibility of DR. First election is of DR, then the next election is of BDR. Yes, correct, Pooja. If DR has failed and your BDR has become the designated router, so even if your original recovers back, it will still not become designated router again because there is already a designated router doing its job. Are we good to jump on to the practical? Okay, first I will show you the DR BDR selections and then we will try a multi-area lab. My Cisco packet tracer must be visible now. Let's see how DR BDR elections happen by creating a similar topology that we just have discussed in the notes. I'll place one switch and four routers around it. So router number 1, router 2, router 3, router 4. We will connect them all to my switch like this. And we are going to place them into the same area. This will be my area 10. Guys, posting links in the group is not allowed. Please refrain from doing that. I'll share the notes. I'll share the article. Don't worry. You'll all get clarification on the procedures and the discussions we are having. So this is a scenario. I have taken area 10 for all the four routers. I will configure them on the network 10.0.0.0/24, let's say. So first we will configure the IP configurations. We are assuming this is R1, this is R2, this is R3, and this is R4. I'll go to R1, CLI. I'll say no to the question. Enable configure terminal, host name R1, interface FA0/0, IP address 10.001.255.255.255.0. No shutdown. I'll share my screen again. No worries. Can you see it now? Is it visible? CLI? Perfect. So host name is configured, IP is configured. I'll take the exit and we will configure OSPF in the next part. Here we have routed to CLI. I'll say no to the question. Enable config T, host name R2, interface FA0/0, IP address 10.002/24, no shutdown, exit. Then we have router 3. We'll go to the CLI. Enable config T, host name R3, interface FA00, IP address 10.003/24, no shutdown, exit. Then I have the router 4. I'll go to the CLI, say no. Enable config T, host name R4, interface FA00, IP address 10.004/24, no shutdown, exit. Now is the time where we enable OSPF on all the 4 routers. I'll go to my router number 1. I will set my router ID manually on this router as 1.1.1.1. Exit. I will go to FA00 and I will configure it in OSPF 100 area 10. Exit. Clear, guys? Then I will go to the router number 2. Router OSPF 100. Router ID 2.2.2.2. Interface FA00. IP OSPF 100 area 10. Exit. Then is my router number 3. Router OSPF 100. Router ID 3.3.3.3. Exit. Interface FA00. IP OSPF 100 area 10. And finally, my router number 4. Router OSPF 100. Router ID 4.4.4.4. Interface FA00. IP OSPF 100 area 10. Then I'll go and check my router number 1 again. Guys, what is the command to check the neighbor table? Show IP OSPF neighbor, right? So show IP OSPF neighbor. I can see I have how many neighbors? 3 neighbors, in which router 4 is my DR, and I am maintaining my neighborship up to what state? State number 7, which is full, correct? Then router 3 is my BDR, backup designated router. I am maintaining my neighborship up to full state. Then finally, we have router 2, which is normal router DR other, and we are just maintaining my neighborship up to two-way. Clear, guys? Now, all your questions or doubts, are they all clear? We can see the priority here is one for all. So by default, it was same for everyone. So how did the election took place? They took place on the basis of router ID. Highest router ID became DR. Second highest became BDR. And then we have router 2 and router 1 as normal routers. So first election is of DR. Okay. Then next election is of BDR. Yeah, that's a usual practice of keeping the router IDs. Like for R1, you go for 1111. R2, you go for 2.2.2.2. That's a usual practice, but it is not necessary. So 4 dots is required. That's the syntax, how your router ID will be accepted. Anuj, IP address is a different thing. Router ID is used for identification of the router. Now you see, this means that you are talking about router 2. That's your router ID. Clear? Now IP on which that router is connected is 10.0.0.2. That's the IP address of it. 100 in the router OSPF 100 command is the process ID. There can be more than one process running on the same router. So for identification of processes, we have process ID. In two-way state, these routers share only neighbor table. They do not share neighbor table. They only share hello messages. And yeah, the routing information is not exchanged. Yes, Michael, even if router 1 and router 2 are just sharing hello messages, but their routing information, their connected networks will be provided to me by my designated router. That's the responsibility of designated router. Yes, Parvez, if you were attentive, then you must have observed I configured the router ID on every router manually. So that's basically what is being used. Exactly, Pooja, because we are on router number 1. That's why we cannot see ourselves as our neighbor, right? Okay, now we have a question. What if we increase the priority value for some router? Let's go for router 3 is already a BDR. I'll go to router 1 only and I will set a higher priority. Config T interface FA00. I'll say IP OSPF priority and I'm going to set it as 100. Exit. And then I'll go to router 2 to check my neighbor table, as I'll be able to find R1 only from a different router. So show IP OSPF neighbor. We can see R1 has got a higher priority of 100, but still, like I mentioned, if DR and BDR is elected, they will not change their role. Still, the router 4 is DR and router 3 is BDR. Clear, guys? Now, how do we refresh this? We refresh this using a command clear IP OSPF process, and we confirm that by saying yes. When I say clear IP OSPF process, all of my neighborships will go down and will be established again. So what I am doing is basically I am just refreshing my OSPF neighborships. Clear IP OSPF process, yes. And finally on router number 4 also I will say clear IP OSPF process, yes. Then again I will go to router number 2 to check my neighbor table, show IP OSPF neighbor, and you can see the changes getting implemented. R1 this time after refreshing, R1 became the DR because 100 was the priority. After that, for BDR election, we again had to look at the router ID. And because router 4 had the highest router ID, it became BDR. Is that now clear to everyone? Otherwise, if you change the router ID for some device, still you will have to refresh the neighborships by saying clear IP OSPF process on all the routers. Perfect. I'll give you 5 to 10 minutes to try these basic configurations. After 10 minutes, we will look at a multi-area lab where we will add multiple areas and we'll try to connect them together. Okay, now we have a concern here that even if a router has a better router ID, still some other router is being selected as DR or BDR. So what to do in that situation? Just clear the process using clear IP OSPF process command and refresh the neighborships. This happens when your all routers are not enabled with OSPF. Let's say only router 1 and router 2 is enabled. So election will take place only between those two routers. Later on, when R3 and R4 will participate, we will not consider changing our DR or BDR. That's why you sometimes see that even a less better router, or we can say a less router ID is selected as DR or BDR. So what to do in that situation? Clear IP OSPF process. Guys, clear IP OSPF command is supposed to be executed in privilege mode. So here, clear IP OSPF process like this. Okay. Are we all done with the lab, guys? Nancy, probably when you were checking the details, your neighborship were getting established and your elections might be taking place at that time. So that's why you see it different in both the outcomes. Just try refreshing it and you will find all of them showing the same details. Yeah, it's fine. Perfect. All right, now it's time to try a multi-area lab topology. I'll create a new file for it. And we'll take multiple routers, which will help me connect different areas. So there will be router 1, router 2, router 3, router 4, router 5. I'll connect one switch with first router and one with the last router. Some end devices here and some end devices here. Let's connect them all. This will be my area 0. This will be my area 10. This is going to be my topology. The middle circle, sky blue circle, will be my area 0. This one will be area 10. And this one will be area 20. The LAN network here will be 210.1.0/24. This will be 210.2.0/24. We are assuming this as R1, this as R2, this as R3, this as R4, and this as R5. The network between R1 and R2 will be 12.10.1.0/24. Between R2 and R3 will be 23.10.1.0/24. R3 and R4 will be 34.10.1.0/24. And here it will be 45.10.1.0/24. Let's first of all put the IP configuration on all these devices. So I'll get started from the router number 1. CLI, say no to the question, enable config T, host name R1. On the interface FA00, I will configure the IP as 210.1.1. No shutdown exit. On the interface FA01, I'll configure the IP address as 12.10.1.1. No shutdown exit. Then I will also create a DHCP pool for my network 210.1.0 with a gateway address as 210.1.1. Exit. Then I'll go to the router 2 CLI. Say no to the question. Enable config T. host name R2, interface FA00, IP address 12.10.1.2.255.255.255.250, no shutdown, exit. Interface FA0/1, IP address 23.10.1.2/24 subnet. No shutdown, exit. We have R3, CLI, say no to the question, enable, config T, host name R3, interface FA00, IP address 23.10.1.3/24, no shutdown, exit. Interface FA0/1, IP address 34.10.1.3/24, no shutdown, exit. Then we have the router 4, CLI, enable config T, host name R4, FA0/0, IP address 34.10.1.4/24, no shutdown, exit. FA0/1, IP address 45.10.1.4/24, no shutdown, exit. Finally, the last router, router number 5. I'll go to the CLI, say no to the question. Config T, host name R5, interface FA0/0, IP address 45.10.1.5/24, no shutdown, exit. Interface FA0/1, IP address 210.2.1/24, no shutdown, exit. Then IP DHCP pool A for the network 210.2.0 with a gateway address of 210.2.1. Are we clear so far what we have done? All right. Now is the time where we configure OSPF. For configuring OSPF, let's understand how the interfaces are going to participate. Both of my interfaces for R1 will participate in area 10. FA00, FA01, both of them. But for R2, FA01 will participate in area 0 and FA00 will participate in area 10. Make sense? So it is R2 which will connect area 10 with area 0. Likewise, R4's FA00 will participate in area 0 and FA01 will participate in area 20. Make sense, guys? So let's begin the configuration. I will begin from, let's say, R1 only. I'll go to R1, config T, router OSPF 100, router ID 1.1.1.1, exit, interface range FA0/0 to 1, IP OSPF 100, area 10, exit. Then I will go to router 2, router OSPF 100, router ID 2.2.2.2, exit, interface FA0/0, IP OSPF 100, area 10, interface FA0/1, IP OSPF 100 area 0. Exit. Then we have the router 3. Router 3's both interface will participate in area 0. So config T, router OSPF 100, router ID 3.3.3.3, exit, interface range FA00 to 1, IP OSPF 100, area 0. Then we have router 4, router OSPF 100, router ID 4.4.4.4, interface FA0/0, IP OSPF 100, area 0, interface FA0/1, IP OSPF 100, area 20. Then finally, this router number 5, both interfaces will participate in area 20. So router ID 5.5.5.5, interface range FA0/0 to 1, IP OSPF 100, area 20. Exit. And that's all what we need to do. We will wait for some time and then we'll test the communication from PC0 to PC2. I can check my routing table on router number 1, show IP route. I can see some OSPF IA routes getting installed. IA means inter area routes. That means these routes are learned from a different area. Okay. So we'll wait for some time and after that we will test the communication. I'll go to my command prompt and we'll try to ping 210.2.2. And we can see the replies are there. From area 10, I am successfully able to ping the devices of area 20. Is that clear to all of us? We have a question that we have intermediate router between area 0 and area 10. Very correct. The router 2 and the router 4. These types of router which participate in more than one area are known as area border routers. Clear? This is called area border router. And a router which is completely participating in area 0, that will be called as backbone router. All the interfaces of R3 are in area 0, so that's a backbone router. Okay. Similarly, if there is a router which connects us to a different domain, let's say OSPF is getting connected to EIGRP. Okay. There is some EIGRP network which I am able to connect with using router 4. So that type of router will be called as ASBR. This is called ABR, area border router, and the router that connects us to a different domain is known as ASBR, which is Autonomous System Border Router. That connects our autonomous system with another autonomous system. Okay. This is some of the terminology that we use with OSPF networks. If there is any queries or doubts regarding what configurations we have implemented, you guys can let me know. Otherwise, you guys can take your time to practice the same. I'm pasting the screenshot of this lab as well as a lab guide with you guys in the Telegram group. Yes, Sanju, autonomous system border router can be any of those routers which is there in OSPF. No specification for that. R1, R2, R3, R4, R5, any of them can become ASBR if they connect us to a different autonomous system. Router 2 and router 4, area 0. Yes, they are participating in area 0 as well as in area 10 and 20 respectively. I've pasted a lab guide for you all. Please try the same and let me know once you guys are done with this or face any questions or doubts in this. Guys, 100 represents the process ID. OSPF process ID can be anything between 0 to 65,000. I am using the number 100. So the process ID is basically which helps us in identifying the OSPF processes. Like I have mentioned, one OSPF router can be running multiple OSPF processes. So to identify them or to differentiate them, we use process ID. Autonomous system is the routing domain, Yogesh.
Yeah, sure, guys. I'll share the notes. But yeah, I quickly want to know, is there any questions or doubts in performing the lab? All right. So I hope we all are good with the concepts of OSPF. That brings us to the end of discussions related to OSPF. In the next session, we'll get started with the VLANs and we'll try exploring some layer 2 concepts. So thank you so much. That was all for today. I hope you enjoyed the class. Take care. Bye bye. I'll see you now tomorrow at the same time.